one of my former course mates, he actually was asked by the dean of the school where he's from, and then he actually said Mauritian, but he said it like Martian, and then the dean thought he was taking a mic.
The Structural Engineering Podcast.
We have on today with the designer, or maybe inventor, of an efficient beam system called the Cellular Hybrid Beam. This is Kee Leung, who started the company Odace. This beam, to me, is the combination of a castellated steel beam, maybe an open web steel joist, and a mass timber element. It's beautiful, efficient, and we'll link everything we can for you to check this system out in the show notes. Kee's company is different than the traditional engineering company you may find after school, so I try to have a conversation that covers quite a lot. So please enjoy the questions, and if you have any question yourself for us or him, you know where we can be reached.
Yeah, so I came over from Mauritius to England when I was 10 years old. I did my undergrad at the University of Sheffield. I did what's called the dual architecture and engineering course back then. So it actually allows you to decide whether you want to become an engineer or an architect after you graduate.
Oh.
So
I like that those are combined. Like in America, right? Most systems are just so independent. The architects don't talk to the engineers.
Yeah, it's really weird. And quite honestly, having been in the industry myself and worked at quite a senior position, I do find that graduates who've got that mixed background to actually work better as part of a team. I have to say, it's like they sort of get what the other profession is trying to achieve. So
Yes.
sometimes when you're isolated, it's all like, architects, engineer sort of thing, sort of thing. Whereas the students who've got a mixed background, yeah, they work better in a team setting. Yeah. So after Sheffield, I got a bursary to study at Cambridge University. I did a master's in sustainable engineering. And then I went into a practice in London. That practice is now been bought out by a larger organization, which is Rambo now, but formerly was called Woodley Bird. A very successful organization. And then I moved around a few of the big practices in London. And back in 2020, just when the pandemic was finishing, I decided to leave and set up on my own. It was a big move. So yeah, I've been on my own for 4 years now, going to my 5th year. So when I left, I had that idea that, we're going to focus a lot on innovation. I found that the word innovation, people say they are innovative quite often. It's very easy to say, but to actually innovate is very, very difficult.
It's big. It's a marketing term in many cases.
Yeah.
It sounds great, so people use it often.
Yeah. So I thought we will really try to innovate. So the idea is to actually partner up with a university and come up with an innovative idea at least every 2 years, maybe 2. Yeah. So the cellular hybrid beam, which is the main subject of this podcast, is the first idea we come up with. Not sure if it's going to be commercially successful, but it does actually. Hopefully you'll branch out into other products and that sort of, it's that sort of idea that I have in mind. I really want to pay respect to the word innovation. It's very difficult to do, but we've got a challenge in our hand. Yeah.
That's a difficult goal to set every 2 year to produce something new, innovative is.
Yeah. We'll see.
Bold. Yeah.
We'll see.
So as you said, the cellular hybrid beam, we had seen on LinkedIn, or I forget exactly, and it's just gorgeous and looked like a great use of material. So that's mostly what we want to talk about. But then looking at your website is really nice, and so we're going to start with questions in that direction. So I just want to ask about the firm Odace, which you had started. So starting there, could you tell us a little bit about the firm and the projects you choose to focus on? And now we have the background of trying to be innovative, but what is your sort of day-to-day if you have a project like that?
But the Cellular Hybrid Beam project is a sort of it's a research project, but it's also more of a passion project. It's not bringing in financiers and money at the moment. In fact, it's probably taking finances from us. Most R&D projects do. So we work mainly in the private residential sector. So right now, it's very busy because spring, we just moved into spring, and every builder and every private client wants to build
Start.
effectively.
Yeah.
So it's super busy. So most of our workload is in the residential sector. I'm trying to branch out into the commercial sector and getting onto larger residential schemes. So that's the next step for us. In terms of my personal day, I've got two engineers working for the company. So myself and two other guys. So I would say about 70% of my time is still on project delivery, and 30% is management and the sort. Yeah. In terms of sustainable projects, I wouldn't set ourselves as just being engineers who do sustainable projects. Again, when you're very small,
Yes.
you got to really be picky. Although I have turned down clients who were a bit yeah,
A little too
well,
needy or wanting things that
yeah,
don't exist. Yeah.
exactly. Oh, that sort of thing, or they were doing things which were not very ethical, or wanted to do things which were not very ethical. That's one of the bonuses of owning your own practice. You can decide who you work for, but we don't. If a project comes in, we still have got to pay wages and that sort of thing. So we're not that picky in that sense.
Yeah.
But I do have to say, because of my background and having studied both architecture and engineering, I do get a lot of recommendations from friends who decided to go to the architecture route. And I've been an engineer now, so they know me. So they'll call me over and say, "Oh, we got this project, or would you be interested?" And having myself studied architecture, part two architecture at the Center of Alternative Technology, there's a lot of architects who work exclusively in low embodied carbon buildings, on low embodied carbon buildings, who contact me and say, well, I want to work with them. So yeah, it's good. It's good in that way. Yeah.
Interesting. And so obviously a lot of my questions here are on low embodied carbon to start, which, as you just said, is not, every project you get to work on, but I think that focus deserves a lot of attention right now. And so that's where my attention is at the moment. So thinking about a lower embodied carbon building, what is the palette that you have to use for materials? Is this a focus in wood construction? And I know we're looking at high-end residential at this point. In the US, almost every house, 94% are wood. That's sort of where we start regardless. Is that where you are designing with?
Yes. In the UK, we tend to use a lot of bricks, steel and concrete. The shift is to use a lot more renewable materials. So that'll be timber, and then obviously steel and concrete are looked at very unfavorably.
Yes.
The onus is to actually, the idea is to actually minimize the use of high embodied carbon material. And when I say minimize, it's even if you look at the timber frame building, which is say 3 stories high, there's no way you can build that building without having any form of, metal in it. So it's really minimizing it and knowing where to place the material itself. For example, the other example I would say is if you're having timber on the outside of the building. I'm not sure how the construction happens in the States, but obviously timber has a shorter lifespan than I would say the brick cladding. So you need to replace it. So I would favor, if I was doing a low embodied carbon building, I would still favor having high embodied carbon material on the outside if it offers a longer design life, and having the sort of more vulnerable low embodied carbon material being protected by the high embodied carbon cladding, if that makes sense. A lot of the sort of, why do you have high embodied energy material, is all got to do with entropy, actually. So, it's like if something is being battered by the elements, you want something that doesn't get damaged or decayed very easily. So that the one will be the one that faces the element. But then most of the time it actually relies on you pumping a lot of energy in it first, so that it stays stable against also climatic effects like heat, like the natural decay. So it's about pumping energy in it so that it stays stable against natural decay.
Do you guys perform a life cycle analysis conceptually of projects to sort of present to the client of longevity available? No. Yeah, that's very involved. But.
Yeah, it's very detailed and like crunching numbers. But then again, I think it's something that could be automated. If you've got like a Revit model, I'm sure there are like plugins where you can automate that.
Yeah. So when you're looking at longevity, I've had some clients that, want a building that lasts 200 years because it makes their life cycle analysis look very good. The average house in the US is 70 years old. The average building is 50 years old. And, we move around as a society. We tear these things down. I tend to lean like lower embodied carbon. I put more personal value there because we don't know if there's going to be a town where this building is in 100 years. And you can't just say, hey, now this building lives for 300 years. I'm good. My LCA is very low. What do you think about from a time frame as you design these? And I know, you talk about a brick exterior will last much longer than wood. But what is that time? Is that 100-year, or is that 30-year versus 20-year versus 10?
Yeah, in the UK, I can't speak about the States. In the UK, there's a lot of the old housing stocks are still there, and it's testament to the material that they use. They use a lot of bricks, and then remember that most of the floors are timber, and I don't think these and most of them are in reasonable condition. Now, if you switched around and say it was a full timber frame, I'm not sure even the floors would survive as soon as you start getting damp in the walls and that sort of thing in the timber walls. So, I mean, the proof is there. It sort of works for itself. Now, in terms of time scale, I think your question was, how do we judge the time scale? I think it would be less about judging the time scale, but say if you had a high energy cladding, could it be reused in the future? Maybe not on the same building, but whether you could dismount it and use it as a panelized system on another building. That'll be my way to approach it. Yeah.
Side note, I was curious about the home age number, but looking it up, you realize this is a complicated thing to think about correctly. The average home in the UK is 50 years old, but 15% of homes are older than 100. But it's not exactly the average age that matters. I mean, in the last 45 years, our population has doubled from about 4 billion to 8 billion about. So we have needed more housing and will continue to need it. This adds a lot of value to the ability to reuse material. This is a big topic that deserves an episode or so much more, but for now, the average home in the UK is 50. We know that for sure.
Yes, I like that concept. The firm that I work for here is doing a presentation tomorrow at the Steel Conference about reusing wide flanges from a hospital. And so it's just basically redoing a building, which would be a great option if that's the only one we have.
I think, and then there's great value in having everything integrated in a BIM model. I mean, one of the advantages that we have is everything is digitized now. So you could have information on building 100 years from now and knowing exactly what material is in there, if it's done properly, obviously, if the model is recorded properly. And it allows you to then salvage out as much material as possible from it when it's deconstructed. Yeah. I can see like a whole sort of marketplace for reused materials in the future, like almost like an eBay of secondhand materials sort of thing for construction. That'll be something that happens, I'm sure.
Yeah, that's true. That would be wonderful to see. Okay, I want to get to the cellular hybrid beam because it is it's beautiful to me, and I love the composite elements here, and that is the reason for giving you a call. So for those that have never seen it, what this thing that I'm trying to describe looks like, how it functions, just a little background of this.
So I'll start it from my aspirations. So
Yes.
I've worked when I was working for the larger engineering firms. I've done quite a few long span open floor offices, and normally in the UK and in much of Europe and possibly in the United States. So the way you achieve it is to have cellular steel beams. So you integrate the service within depth of the beam. So you increase the depth, basically. So the depth of the beam now includes the service zone. So you maximize the depth of the beam, meaning that it can span longer than if you were routing the services underneath it. And then the other thing that you do is you mobilize composite action between the slab and the beam itself. So you effectively have like a super deep beam with a big compression flange at the top. That's normally what happens. Now, with timber, this is not that easy to achieve. Basically, if you try to puncture too many holes in a timber beam or a laminated timber beam, if you puncture too many large holes, then the beam is going to be very prone to splitting. You can't actually bend it too much. And then you could you can quite easily mobilize composite action between a mass timber slab and a glulam beam. That's fairly easy. You can use a lot of modern connectors now, or even glue them together. But what people have tended to do is to take a steel beam and try to mobilize composite action between the steel beam and the slab itself. And that's purely, and a lot of it has got to do with achieving the longer span that a timber beam can't give you, but also trying to get service holes for a steel beam, because you can get service holes for a steel beam fairly easily, and you can't do that in timber. But then with regards to achieving composite action between the timber and the steel is actually quite complex and not very efficient. To get that composite action going, you've got to have loads of shear connectors in between the slab and the beam itself.
Yeah.
Right. And if you imagine all the holes are drilled into the steel, and then you try to line up all the holes from the slab onto the steel, it's very unlikely that the holes location won't match. You got like a 12-meter long beam, and the timber slab itself is going to move according to its moisture content. It's very difficult to get it all lined up. And then the other thing, when I said it's not a very efficient structure, because even if you manage to achieve composite action between the slab and the beam, the top flange of the beam is actually very close to the neutral axis of the composite section. Right? So if you look at the neutral axis where it is in relation to the composite slab,
so it's not doing anything.
It's not doing anything in its final state. So that's one disadvantage of it. And then the further disadvantage is if you've got your slab above, your beam below, and you've got all sorts of connectors connecting the steel beam into the timber slab. In an outbreak of a fire, if ever the beam gets hot, even though it's intumescent painted, the temperature of the beam, intumescent paint only starts going off at around 200 degrees, maybe a bit less. But then having these shear connectors straight from the beam into the slab above is actually a straight path for the heat to be connected into the slab. So unless you encase the steel beam completely, you're not setting yourself really well. So what I thought of doing then is I'll show you. I've got the mock-up model of it, so I'll show the viewers. So it's this system here. So basically, you've got your steel element here, right? So the idea is to form a composite beam in the first instance. So that would be a piece of timber panel mass timber panel. So it could be either laminated veneered lumber or even cross-laminated timber if you wanted to. The idea for the timber is that it can carry the stress in two directions around the opening. So that's why you want the layers to be aligned orthogonally to each other. And then what you do is you'd connect the bottom piece of steel to it, which is cut from a universal beam. So you take a normal I-beam, cut it in two in a sinusoidal wave shape.
Yeah.
And then you connect, and then you join the piece of timber and the steel together with bolts or any other fixing that would allow a horizontal shear force transfer in between the timber and the steel. So then once you've done that, the stressors can work itself through the timber in two directions and can work itself in the steel. You're effectively creating a steel timber truss, all right? But you're doing it in a very efficient way. Now, the issue with steel timber trusses or timber trusses in general is timber to timber connections are actually very weak, right? I'm not sure if you design it, but they're quite weak.
Yes.
And having to form trusses in timber, you would have to join in a lot of small elements together. So it's quite time consuming. Whereas here you're just taking a mass timber panel and cutting it in waveform. So you can imagine if you were to put that on a table, piece of timber, you could mass produce it from a mass panel. You could simultaneously cut different sections out of it. And you do the same with steel and then join them together. So it's a lot more efficient. There's a lot less handling of the timber. And then the holes between the timber and the steel would be perfectly aligned if you were doing it in a CNC, on a CNC table. That's the other thing. Then the third element of it is, again, going back to when you're having timber trusses, you can imagine each small element of a timber truss, in the event of a fire, you burn very quickly because there's a lot of exposed surface area, right, for each strut and tie. Whereas if you got one singular piece of timber, right, the actual surface that's going to be exposed to fire is quite small compared to the volume. So that's another advantage of it. And now what we effectively have done also is to make sure that you've got a timber to timber interface between the slab and the beam. So then you can do any of the connections from above. So you just
no issue with screws.
Yeah,
yes.
Exactly. So
how much from the scale there? How much of the top of the beam is timber? Is it about a third is completely timber?
So that's a third, correct? Yeah, correct.
Yeah, okay.
Yeah, but the I have to say the top section here, the function, it's actually a function of how deep your screws are. So even if you're having a deeper beam, it doesn't necessarily mean that this top section is going to get deeper. It's just a function of how deep the screw embedment needs to be.
Yeah.
So if you make it deeper, it's quite likely that you could keep that top section to the same thickness but make the beam deeper. It all depends on geometry. Yeah.
Yeah. And so the bolts in the middle, I assume that's for shear flow. Assume it definitely is. And then how many of these beams that you built, what does that connection typically look like? Is it a dozen, half-inch diameter bolts through there?
So these ones, I mean, again, they are subject to further optimization, but on some of the experimental models that we had, these beams are 350 mil deep, and they manage to carry 2 point loads of 7.5 tons. So that's roughly 15,000 pounds, I think.
Yeah.
7.5 tons point load applied at third span. So in total, 15 tons. And they were 350 mil deep. So yeah, quite a bit. Now coming back to the shear connectors in here.
Yeah.
Again, they are subject to to optimization, you'd have most of them here. For the sake of just doing the experiment, we had all of them similar, but you could reduce number as you go towards the middle. So most of the shear flow is going to be at the ends. So as modeled right now, that was what we used in the proof of concept model. So they were half inch. I'm trying to convert millimeters into inches. So
Thank you.
half inch bolts, grade 8.8, and then there were 10 of them in each connection.
Okay, interesting.
Yeah.
And you had shared a video of this beam being tested, and it just looked like it performed very elastically. What is the failure? Once you're well beyond the rating of this, is it the bolt bearing on the wood that is what starts to yield a little bit?
It's actually the wood wanting to split. Yeah. So as it starts bending, the wood would start to split towards the end horizontally.
Yes.
So that's the failure mode that we've observed. And there's also some tension cracking on the, if you imagine these being a strut and tie model, there'll be tension on these diagonals. So you would start noticing them splitting in tension and opening up. Yeah.
Oh, interesting. Okay.
Yeah.
What sort of projects have you been able to use this on so far? I know this is a development. This is a totally different idea than just, hey, let's build this beam for this project. But where have you been able to put it?
We haven't been able to use it yet, although if any of your viewers want to try it, we're happy to actually share information with you. But we got some queries. I had a query last week about a sports hall in Belgium. So hopefully we'll find a project where we can experiment it on. It's still
Exciting.
being worked on. So yeah.
Okay, so then this question is different, but what sort of spans do you expect to be able to get out of this? We all know our timber suppliers, a CLT panel is only going to be 60 feet from a manufacturing standpoint, around 60. Each supplier does it different. It's not like they can go 60, but that is as far as they could possibly go. What sort of length are you expecting you might be able to get out of this for typical residential loading?
Sorry, I should probably preface this. I don't expect it to be used in a residential setting.
Okay. I'm using it as light loading. So
the likely use of it is going to be in open plan offices where you need large column grids, and things like sports halls where you need long spans. Yes. On residential buildings, it's less attractive because residential buildings, they tend to be a bit more cellular than offices. And I know the in the US. Sorry.
I was just, if this was my house, I'd be very proud. But I understand that is not the typical. Not everyone is an engineer here, so.
Yeah, I might try it on one of my on my own house. We'll see.
Yeah.
At one point.
Okay, but the grid of a larger span, are we talking like 15 meter kind of?
We're pushing towards things like 12 meters, 12 by 10, 12 by 9 meters, something along there. It'll be similar spans, maybe a tad less than what you normally achieve with composite concrete and steel beams. Yeah, so it's sort of almost like a direct competitor in that region. Yeah.
I think about it when I saw this photo, the castellated steel beam, which I think you had said cellular, I think, steel beam earlier. Is that what we might call castellated, where you cut these diagonals in a beam and then shift it over, and then you get And so, what is the openings that you might expect out of this member? Like, if you have a 1 meter deep beam, you have about a 1 by 1 meter duct every.
Yeah. So right now, based on the models that we've done, the actual proof of concept models, we've achieved 0.6. So which is pretty good. But we're trying to actually increase that in the next phase of testing. And typically, the wavelength in between each opening, we try to keep it quite far apart. Currently, it's about 3 times the depth of the beam. Typically, that's what we want it to be. I have to say we're tweaking the design right now. So the final product, if ever it was commercialized, might look quite a bit different from what you're seeing. Just to make it a lot more robust. Fire seems to be one issue that we have to address fairly quickly if we wanted this to take off. The feedback that I had from a lot of consultants and contractors would be the fire issues. Yeah, we need to address that fairly soon.
Yeah, that's the few people that I've shared this photo with. That's also what they asked, because fire in timber is an element, but it's also the people's first questions, right? Because we just think of wood, what goes in the fireplace. You know, we have managed to get around this in timber structures, but I want to ask the wood that you're using. Now, I know you were in Europe, and so maybe you have different categories of wood. Maybe you certainly do. Are you using a higher grade wood, or what style?
No, it's the same. It's your typical grade of timber. Actually, for the beam itself, you could, in theory, use a weaker timber. I'm not sure how the grades are classified in the US, but in the UK, it's C24. I think the Canadians use the same sort of.
Okay.
Same sort of.
I will add a little link to what that means for us. Like, we look at visually graded, and I don't have the numbers memorized very well, but we just do like a V5 is visually graded, 5 capacity. I don't know how this exactly transitions.
Actually, on the grades, just as a slight detour, so to actually connect the panel onto the beam itself, in the experiments that we've done, we've used what's called a hooked plate connector from Orthoblas. So this is basically a very thin steel plate, 0.5 millimeter thick. It's got like little hooks on both ends. So the idea is that you lay that on top of the beam, and then the slab comes over, and then the slab gets laid, and then you screw through the slab through it, because it's, if you use
thin enough that you can get screws through,
and then it pulls the slab and the beam together, and then this actually bites into both pieces of timber and locks it in place. So then you have a shear transfer between the slab. So it allows. That's the other point with it. We intend, in theory, you could engineer a small rig that would banging those screws very quickly on top of the slab. So it just tracks on the slab and then just insert these screws very quickly. So you could automate the process on site if you really wanted to.
I think that'll make construction much easier, which will maybe get this more active. Interesting. Is the future goal, the daydream goal, is this to have this system as a tabulated beam where you say, hey, I've got this load, it's going this far, I'll open my book and say, okay, here's what I should use? Or is this a design every time you run the numbers like it was a truss instead of like it was a 2x6 and we just look at a book and say it goes this far?
I think it could be for both, to be honest. Like, you could be for both. I mean, there would be, even if you were to use a tabulated approach, there's no reason that would restrict you from having a more bespoke approach. If you had a particular building setup, particular building configuration, like an extra long span, you could basically design it from scratch. Sorry, the reason I showed this to you, I should probably say, we're talking about timber grades. So these type of connectors actually don't work well if the timber is too dense, because the teeth actually don't bite into the timber. So you want the timber to be sort of medium density, and even towards a lower range, it probably works better. to achieve the shear transfer. If you were using, say, too hard of a wood, then the teeth won't bite into the wood. So you got to factor that in. That's why when you mentioned it,
Okay.
it
Yes.
sort of prompted me to talk about it. Yeah.
I wonder. It's probably very similar to pine. I mean, I know you have pine as well, but that is often our lower grade is pine lumbers. Do you have a time framing? Is there like we want to be able to make this producible within a year if you like the way it looks?
So right now, there's a student at Cambridge University who's doing his doctorate on it, and the idea of the doctorate is to produce design guidance for that particular type of structure.
Yeah.
Now,
how far along is he on the doctorate?
He's just about to finish his first year, so he's got 2 more years.
Oh God! Oh yeah.
To finish. Now, I should say, if there was a project that came along that was going to use it in a setting where fire isn't too much of a consideration, i.e., for example, if you're using it in a roof, right, support a roof, like a long span roof. I'm not sure what's the building regulations like in the US, but in the UK, roofs don't necessarily need to be fire protected. So if you were having a sports hall, for example, and you're forming the roof, it doesn't need to have there's no defined fire resistance for it. So if you were in that setting, you'll probably be able to use the beam straight after the doctorate is finished, or even now, if we have enough data to design it. But then there's a second phase of study where we have to assess its fire performance. And to do that, we might have to tweak the way the beam is put in together, and even maybe change the way the timber is actually formed in a factory, which might lead on to the second innovation that the company works on. So I was telling you earlier about trying to release an innovation every 2 years. So it might actually branch into that. And make both products work together. So changing the way mass timber slabs are produced, and then marrying that to how to use steel as part of a mass timber floor structure. Yeah.
I like this concept, and a really nice use of materials and their strengths, to build an efficient system that is not all wood because it looks good, or it's about building efficiency here, and I think it's going in a great direction.
Thank you very much.
Well, that is all the questions I have. We're going to link everything that you mentioned in the show notes below, and I'm going to provide as many photos as I possibly can. But I think this is a beautiful system, right? My background is in architecture, and this part of it really reaches out to me, as I'd love to see this used more. So, but Fatki, thank you very much for joining us today. And
thank you.
Yeah, looking forward to seeing where this goes.
Thanks, Max. Thank you very much.